All right, guys. Last class, we have talked about some preliminaries and brush up our discrete mathematics topics like set, function. Today we'll continue with some more preliminaries, and then we will go to proof techniques. Okay, so let's start. Subset and superset. Let's take A equal to 1, 2, 3, 4 and B equal to 2, 3, 4. So if you observe this two set, then you will see all the elements in B are also present in A. In that case, we say B is a subset of A. But in this case, we are pretty sure that A has one extra element, which is nothing but A. When we are pretty sure there is at least one element more in a set than the subset, then we use the term called proper subset. When we are pretty sure. And this one is called superset. On the other hand, let's take another set. A dash 1, 2, 3, 4. B dash is also 1, 2, 3, 4. Here, all the elements in B dash are also present in all the element in A dash. So we are sure B dash is a subset of A dash, but there is always a chance of equality. They might be equal. So whenever we are not certain whether A dash and B dash equal or not, that time we put a equal sign under the set, and that time we call it only subset, and still it is superset. Is the concept clear to you guys? When there is a chance of equality, whenever there is a chance of equality, we don't know the answer of this, we use the equal sign under the set because they might be equal. We don't know. That time it is only called subset, and superset remains the same. On the other hand, we are pretty sure that superset has at least one more element. Then we use the term proper subset, and proper subset notation does not have a equal sign under it. Yes. Tell me, what is the question?
Sir, since all the elements are there in A of B, so isn't B not a superset as well?
Yes, it is true. Yes, it is true. In this case, when A dash and B dash are all equal, A dash and B dash both are equal, that time we can say A dash is a also subset of B dash. If we know they are equal. True. Okay? True. Because
Yes, sir. Thank you.
A dash equal to B dash, it can also equivalently write A dash is a subset or equal of B dash, and B dash is a subset of equal of A dash. This expression and this expression are same, equivalent expression. Only in the case when A dash and B dash are same. Is it clear to you?
Yes, sir.
Okay. So whenever there's a question of equality, we don't know the answer, we always use subset notation, under it A equal. Otherwise, we use, when we are pretty sure superset contains at least one more element. When we are pretty sure they are not equal, that time we use proper subset. Okay, guys? Okay. So now, number of if A equal to 1, 2, 3, 4. How many subsets are there of A? How many subsets of A?
5, sir.
5. Is there any more answer?
For one.
Only one subset.
No, more, sir. More than
4.
5. No,
More
more
than
than
5.
5.
More
For
than 5.
one.
What? One. Only one subset. Why there is only one subset?
Yes, sir. Subset means like all of the elements
Sir,
should be there, right?
16 subsets.
16 subset. Another person says 16 subset. The correct answer is 16. Can you prove that it has 16 subset? Okay. Can you tell me one subset of this?
Itself.
Let's take 1 comma 4. Definitely it is a subset, right? Because 1 comma 4 both are inside A. It is a subset of A. Do you agree with me or not?
Yes, sir.
Okay, sir. Now, how many elements are there in A? 4. 1, 2, 3, 4. In a subset, one might be present, might not be present. B might be present, one might be present, one might not be present. Two might be present, two might not be present. Three might be present, three might not be present. Four might be present, four might not be present. So using different combinations of 1, 2, 3, 4, we can create all the subsets, right?
Yes,
For
yes.
example, in this case, 1, 4, 1 is present, 2 is not present, 3 is not present, 4 is present, right? So in this argument, all the numbers are possible for different combinations. We can get total number of subsets. Do you agree with me or not? Tell
Yes,
me.
sir.
So how many different combinations are possible for this argument? How many choices
16,
there?
sir.
2. How many choices there? 2. How many choices there? 2. How many choices there? 2. Do you agree with me or not?
Yes, sir.
So it is nothing but a big task is divided to subtasks. 2 star 2 stars 2, which is nothing but 2 to the power 4, nothing but 16. So we get the answer. Do you agree with me or not?
Yes, sir.
If A n has n elements, A1, A2, an, how many subsets are possible?
2 to the power n.
2 to the power n. So How many subsets of A? 2 to the power number of elements in A. That would be the answer. All right, guys.
Sir, এখানে কি null set consider করতেছে?
Of course, because
Right.
what is null set? Null set means we did not take 1, we did not take 2, we did not take 3, we did not take 4. Nothing. We take nothing. So this is also a combination. Am I right?
Yeah, yes.
Yes. So let's go to next topic. Power set. Set. Power set is a set. Remember, set of all subsets. Power set is a set of all subsets. Set. It is a set. So let's take A equal to 1, 2, 3. How many subsets are possible? 2 to the power 3 equal to 8. So let's list down all the subsets. First one is null set or 5. Second one is 1. Third one is 2. Fourth one is 3. So this is 0 element subset. This is 1 element subset. And let's go to 2 element subset. 1, 2, 1, 3, 2, 3. This is the 2 element subset. And finally, I have 1, 2, 3. 3 element subset. So how many subsets are there? 1, 2, 3, 4, 5, 6, 7, 8. So the formula verifies. All right, guys. Now tell me, out of all this subset, which one is actually proper subset and which one is only subset?
Sir, proper subset element বেশি থাকে স্যার।
হ্যাঁ সেটাই তো proper subset
Sir,
একটা
except for
Sorry,
1 to
so
3.
proper.
All is
Except-
for 1 to 3.
except 1 to 3
All are subset.
all are
Proper subset.
all are
subset.
proper subset. Only this one is subset.
Yes.
Good, very good. Now power set of A denoted by PA is nothing but set of all these subset. So 5, 1, 2, then 3, then 1, 2, 1, 3, 2, 3, and remember it's a set. All right, guys. So this is called power set. Now let's go to another topic, which is called cardinality. Cardinality is nothing but number of elements in a set. Cardinality of A is nothing but A denoted by bar before left side and bar after. There is a bar on the left side, there is a bar on the right side. So if A equal to 1, 2, 3, what is the cardinality of A? Remember elements.
3.
The cardinality of A is 3. Now, what is the cardinality of this power set? Elements, remember, elements. Number of
sir.
elements in 8. So, cardinality. So, we can say if A has n elements, let's say an has n elements, then cardinality of A is what?
Hence,
N. And power set of A, its cardinality is what? 2
So
to the
2 to
power
the power
n.
n.
So we are done with theoretic theorems. Now we'll start proof techniques. Do you have any question? You can ask me. Do you have any question?
no, sir, it's clear.
It's clear. Now tell me, why do we need proof? Why do we need proof? Tell me. Why proof is important? Huh? Why proof is important? Tell me. If somebody loves another person, do we need proof? We are Sadman Wasif.
Yes,
Was,
yes, sir.
let's
To
assume a girl.
verify.
No, let's forget about proof techniques of logic and other stuffs. Let's think this, sir. We are Sadman Wasif.
Yes, sir.
Let's assume a girl loves you. Do you need proof?
Yes, sir.
You need proof. How can she prove she loves you? Giving you expensive gifts. Eh?
Yes,
So,
sir.
human mind is actually very. হ্যাঁ কেউ কিছু বলবেন মেহরুন নেসা বলবেন কিছু বলবেন না so human mind is very instinctive okay so they actually understand a person likes him or not or a person likes her or not just by talking only one sentence human mind is more developed it is a surreal things we don't need proof of love. We do not need proof of hatred. Okay, but logic is different. Logic does not take care of this kind of things. Logic does not pay attention to actually the emotion. So that's why proof technique is important. So what is proof technique? What is proof? Tell me. What is proof? How do we prove something? Tell me. How can you prove something? Let's assume I says 4 is a even number, is an even number. How can you prove that one? 4 is an even number. How can you prove that one?
So we can prove this based on existing evidence, like 4 is divisible by 2. So,
Okay,
like,
wonderful. So we can write 4 is nothing but 2 plus 2, which is nothing but 2 into 2, which is divisible by 2, and that is the definition. That is the definition of even number. So 4 is even number. Done. Am I right or not?
Yes, sir.
Okay. So
Yes, sir.
whenever I say 4 is an even number, whenever I say 4 is an even number, I just assume it is an even number. That time it is called conjecture. Okay, without proof. Without proof, saying something, it is called conjecture in mathematics because you did not verify whether it is true or not. Remember, what is the word? Conjecture. But here I have already proved that 4 is an even number. Then it would become theorem. Now I can say 4 is a even number. Okay? Without proof, saying something is called conjecture. That means it is not verified yet. Whenever I am done with the proof, it becomes a theorem. Only a theorem can be used to prove other theorems or other conjectures. No conjectures can be used to prove other conjectures. For example, now if I give another conjecture, 8 is an even number. So how can you prove that one? 8 is an even number. We can use this theorem. We do not need to go very basic. We can use this theorem now because we have already proved this. So 8 is nothing but, let's make 8টা খুব বেশি ইয়া হয়ে যায় 12 করে। এটা আসলে একটা প্রয়োজন হয়। 12 is a even number. 12 is an even number. So 12 can be written as 4 plus 4 plus 4, which is nothing but 3 into 4. We know that it is even. So definitely the whole thing is even. Am I right or not? It is even.
Yes,
So it
sir.
is divisible by
Yes.
2. So the whole thing is become divisible by 2. So it is even. Now it also becomes a theorem. Now, what is proof techniques? Proof techniques is jumpings, this jumps. Using this theorem, proving this conjecture, the jump I made, the logical jump I made, those are called proof techniques. Jumps. This jumps is nothing but proof techniques. How do we make jumps? Okay? Logical jumps. Logical jumps are called proof techniques. All right, guys. Do you have any question? You can ask. কোশ্চেনটা আসা উচিত। কোশ্চেনটা কি হবে ওয়াসিফ? The question is, sir, we understand we use simpler theorems to prove complicated theorems. But now you should ask me the question, just sir, if we use a simpler theorem to prove any complicated theorem, how can we prove that simpler theorem? Then if you use another theorem to prove that simpler theorem, then how can you prove that simpler theorem? So this way it will continue, simpler theorems. How can you prove the
Right.
root theorem, the most simplest theorem? Am I right or not? Am I right or not?
Yes. Yes.
So
Yes, sir.
let's start with formal proof techniques. Before starting proof techniques, we need to know few things which are always considered true. The very basics. Now, one is called axioms. Second one is called principle. And third one is called axioms, principle. And third one is called definition. These three things, we can never prove axioms. We can never prove principle. We can never prove definition. But those things are always considered true throughout these jumps. Okay, so those are the self-evident truths. Did you get it? So we have already raised chicken and egg problem. That's if this chicken comes from that egg, how come that egg comes from? So these are the very basics. These are the ultimate egg of proofs. Did you get it? Those things are always considered true. Do you have any question?
Sir, মানে হচ্ছে like we do not question the basic truths or the basic
You can
principles.
question. No, the thing is, you cannot prove these things, the basic truth, the axiom, principle, and definition. But those are very, very simple. The very, very simple and natural consequence of nature, natural laws. That's why we can always consider those are true. Okay, guys?
Okay, sir.
You can question if somehow, for example, if you think that, let's assume I want to prove something. You say the whole thing is actually my definition. If you say like this, okay, then there is no need to prove anything. Am I right? For example, there are infinite prime numbers. You say, I consider the definition of prime number is there are infinite prime numbers. Then we do not need to prove there are infinite prime numbers. So those things cannot be axioms, principle, or definition. The definition, principle, and axioms are very, very simple things, very, very natural things. Those can be considered always true. Did you get it or not?
Yes, sir.
So let's give you some example. For example, let's give you a definition. What is definition? For example, any number divisible by 2 is even. Definitely, it is the definition. Can you question about that one? I define even number this way. So what else you can question? Am I right or not?
Right, sir.
So this is the definition of even number. So how can you question? I define even number this way. Any number divisible by 2, that is the even. Any number divisible by 2, that is the definition of even number. So you cannot question about it. Now let's go to axioms. Simple facts to build a math system. Simple facts to build a math system. It is called axioms. For example, do you know natural numbers? What are natural numbers? What are natural numbers?
Sir, 1, 2, 3 to n.
It is starting from 0, 0, 1, 2, 3, up to infinity, right? Those integers are called natural numbers, starting from 0. Okay? So how can you generate the natural number set? Tell me. How can you generate the natural number set? How can you generate this set? Using a machine or using your calculation. So we can use axioms. Axioms of NL. Number one axiom. 0 and 1 are NL. Right? My second axiom is adding 1 with last NN, we get next NN. Do you agree with me or not?
Yes,
Do you
sir.
Yes,
so
Yes.
0 natural number, then 1 natural number, we add with last natural number. So 1, we add another 1, we get 2, the next natural number. We then add another 1, we get 3, we get the next natural number. We can add 1, we get 4. Next natural number. This way it will come. So these two axioms actually create natural number set. So it is enough to have these two axioms to create natural number set. So you can consider this is a true things. And it is very natural, like simple facts, very natural. And it creates the math system. So this kind of axioms you can consider always, these two steps. Is it clear to you? Okay. Now, what is
স্যার একটা
principle?
প্রশ্ন ছিল।
Go ahead.
আচ্ছা, can we say যে ওই যে axioms এর part 1, 0 and 1 are NN? Can we say this is a definition?
No, it is not. You can say it's a definition. Yeah, simple definition. That can be also true. Yes, you can say that.
Okay,
You can also consider 2 is also a definition. Don't worry.
right.
Creating the next natural number. So those are interchangeable. You're right. Your observation is good. Yes.
Okay.
You can also consider axiom is a kind of definition. True. True. Very true. Can we go to principle?
Yes, sir.
So principle is some simple natural fact can be considered true. Some simple natural fact can be considered true. Can you give me an example of principle? Can you give me an example of principle? You people know a very famous principle from your discrete mathematics. What is that? Guys, can you give me an example of principle?
Sir, yellow is the color.
Well, how come it is a principle? It might be a definition, but it is not a principle. It might be a definition, but it is not a principle. It is not a natural fact which can be considered always true. So let's give you an example. Pigeon Hall principle. Do you know this principle? So let's give an example. Consider there are 4 holes. Okay, guys? My drawing is very well. Okay, so I do not want to disappoint you. My drawing is very well. I always, whenever I remember that my drawing is very bad, I always remembered a very funny incident. Once, my wife asked me to draw her. Then actually I draw another girl's picture.
Oh, yeah. I remember. He told us.
My drawing is so bad. Another time he asked me to draw a actually swan. I draw actually chicken. So my drawing is very bad. So don't get it disappointed. So let's get back to study. Let's assume I have 4 holes and I have 5 pigeons. Then I can say at least one hole will contain more than 1 pigeon. Can you prove this actually? At least one hole will contain more than 1 pigeons. Can you prove that actually? No, it is not possible to prove. But it is a very natural fact. How? Let's put this pigeon in this hole. 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 So all the holes are filled up. Still, I have left 1 pigeon. So if I want to incorporate this pigeon in one hole, It should be somewhere here, 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 and here. So of course, definitely, one hole will contain more than one digit. Is it clear or not?
Yes, sir.
Yes, sir.
Clear.
Okay, so you cannot prove this one, but it is so natural, we can consider it is true. Now remember, A proof is more elegant when it use less axioms, principles, definition, and other theorems. The less you use those tools, it becomes more elegant. Okay, guys? Do you have any question? You can ask. So these are the chickens. These are the chickens, or the first egg, first chicken or first egg. Using this, you are going to prove simpler theorems. Then using those, you are proving some more little complicated theorem. This way it will continue. Now ultimately you prove the theorem you want to. Okay, guys? So that's the thing. So it is something like this. Using axioms or principles or definition, you prove simple theorems. Then using this, you prove more theorems. And finally you prove the ultimate theorem. So these are the jumps. 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 So these jumps are called proof technique. How can you jump? Logically valid jumps. Okay, guys, can you tell me some proof techniques? Can you tell me some proof techniques?
Induction.
Okay, fine. Logically, so proof technique is nothing but logically sound and valid jumps from one math statement to other math statement. So can you give me some examples of proof techniques?
Proof by contradiction.
Okay, induction, contradiction, what else?
Truth tables.
Truth table, yes, is a kind of proof technique. It is called proof by exhaustion. Anything else? So let's give you the example. The first one is called direct proof. Second one is called mathematical induction. Third one might be called uh, proof by contrapositive. Fourth one can be called proof by contradiction. Number 5, proof by construction. Proof by non-construction. Then proof by exhaustion. So these are all the most famous proof techniques. There are a few more: probabilistic proof, then proof by figure arguments. Those things are also there. And all these proof techniques must be logically sound. So let's give one example of each of these categories. What is direct proof? Do you have any question? Do you know the method of direct proof? What is direct proof? What is direct proof? Can you tell me? Direct proof is nothing but proving using only the very basic things. That means axioms, principles, definitions, and proving using only axioms, principles, definitions, and simpler theorems. So let's assume twice A plus twice B is an even number for integer A and B. How can you prove this? Using direct proof. Tell me please. Guys, don't sleep.
So 2 is even, and when you multiply even with n number, it will become even.
So what is your axioms, principle, or definition? Definition, we know that. We know the definition of even number. Fine. What axioms you are going to use?
Sir, addition of two even numbers is an even number.
And if you want to use that one, you have to prove that one. So let's use these axioms. Distribution of numbers. If A, B, C are numbers, then what can we say? A multiply with B plus C, it is nothing but AB plus AC. Am I right or not? So we can go from here to here, and we can also go from here to here. So what is 2A plus 2B? What can we write? Tell me.
2 common A plus B.
2 common A plus B, and it is divisible by 2. Do you agree with me or not? That means it is even, so it is also even. Done. Did you get it? Here we use only the definition of even number and distribution of number axiom. Do you have any question? You can ask me. No question? Got it? Got it?
Yes, sir.
Got it.
Yes.
Okay. Now let's go to next one. Mathematical induction. What is mathematical induction? What is mathematical induction? What is mathematical induction? Please tell me, what is mathematical induction? It is nothing but domino effect. Domino effect. So what is domino effect? Let's assume we have placed many blocks this way, and it continues up to infinity. So if we hit this one, because of the domino effect, it will hit this one. Then this one fall, and this will hit this one. This way, ultimately, up to infinity, every blocks will fall. So this is nothing but it is called domino effect. Am I right?
Yes, sir.
Yes.
So mathematical induction in proof mimic this domino effect. We have a start point, which is called base case or basic. Then point, we prove the statement. Then there's another, the next step is called inductive hypothesis. We will consider at some point and it is true, and it is true, and based on this we will prove m+1 point it is true. Then the conclusion is statement is true for natural numbers or integers from start point up to infinity. Did you get it or not? Do you have any question about mathematical induction? Guys, are you sleeping?
Hypothesis যেটা point 2 ওটাতে হচ্ছে কি I had a question যে ফার্স্ট এর দিকে হচ্ছে the first point we start from the base case ওইটা তো হচ্ছে গিয়ে প্রথম যেটা বর্ণ হয়েছিল যে
মনে করেন এক, let's call this way 1 2 3 up to infinity. Okay, then we prove for 1. Then
done.
So for taking an arbitrary point, we take any some arbitrary point m. Using this, we are proving it is also true for m+1. Okay, guys.
Yes.
Then ultimately it is true from starting point up to infinity. Why? You can say, sir, how can you consider a arbitrary start point? Because we have already proved for start point 1, right? So if we can prove if m is true, m+1 is also true, then actually we can place 1 instead of m, then we get 1 plus 1 equal to 2. So it is also proven for 2. Now we can consider 2 is the arbitrary point, and using this fact we can prove it is true for 3. So this way it will continue and the domino effect will last forever. Is it clear to you guys?
Yes, sir.
Yes, sir.
Okay. So let's give you an example. Prove that 1 plus 2 plus ... up to n is equal to n into n plus 1 divided by 2. So how can you prove that one? What is the first step? Start point. For n equal to 1, what is LHS? What is left hand side? For n equal to 1, what is the LHS? 1. What is the RHS? 1 into 1 plus 1 divided by 2, which is nothing but 1. So LHS is equal to RHS. Okay, guys?
Okay.
Number 2, inductive hypothesis. Assume for n equal to m, it is true. What is the meaning of this? 1 plus 2 plus ... up to m is nothing but m into m plus 1 divided by 2. Do you agree with me or not? Now, if n equal to m plus 1, then actually 1 plus 2 plus dot 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 plus m plus 1. What is this? What is this? What is this? This is nothing but up to this is m into m plus 1 divided by 2 plus m plus 1. Do you agree with me or not?
Yes. Yes, sir.
Then take the common denominator. It becomes m into m plus 1 plus 2 into m plus 1. It becomes m plus 1, m plus 2 divided by 2. Now here put n equal to m plus 1, then it would become m plus 1, m plus 2 divided by 2. So we have proved for n equal to m plus 1. So proved. Do you agree with me or not?
Starting point is sir for n equals to 1. LHS to 1 can have sir.
ধরে নিলাম একটা starting point. After 2 থেকেও you can start.
Oh, okay.
In that case, it would be true from 2 up to infinity. এটা স্টার্টিং পয়েন্ট ধরে নিয়েছি আমি 1 কে স্টার্টিং পয়েন্ট I have considered 1 as the starting point. Okay guys, do you have any question? Done? Now let's go to next proof techniques. Proof by contraposition. So what is contrapositive? What is contrapositive? Huh? Tell me. If P implies Q, what is the contrapositive of this? Tell me.
So not Q implies not P.
Not Q implies not P. So this is the contrapositive. What is the relation between these two? What is the relation between these two? They are actually same statement, but different form. Same statement, but different form. This statement truth table and this statement truth table are same. So they are actually same statement. Okay, guys? So instead of proving this, we are proving this. Then as proving this is nothing but proving this, it is also proved. Can you give me an example? So let's try this. If x squared is an even number, then x is also even number. We're trying to prove this using contrapositive. Okay, guys? So what is the contrapositive of this? What is the contrapositive of this? It is nothing but x square. This statement means x square is even, implies x is even. What is the contrapositive? What is the contrapositive of this? Tell me. What is the contrapositive of this statement? Tell me, please. P implies Q implies not P. That is the contrapositive. So not x is even implies not x square is even. So x is not even or x is odd implies x square is not even or it is odd.
Or
Do you agree or not? So instead of proving this, we are trying to prove this. So if x is a odd number, odd integer. Then what is x? X is equal to twice c plus 1, where c is integer. Do you agree with me or not? Yes, sir?
Yes, sir.
So what is the square of x square? What is the square of x? X square is nothing but twice c plus 1 whole square. So what is this? 4c square plus twice c plus 1. So what is this? Take common of twice c. You get twice c plus 1 plus 1. So what type of number is this? It is a
Odd number, sir.
It is odd number. No, up to this. Yet to here. Twice c into twice c plus 1. What type of number
That
is
will be
this?
even, sir. Even.
Divisible by 2, so even.
Even number.
So
Yes.
what is the remainder? Remainder would be, the overall number remainder would be
1, sir.
1. So it is definitely, this number is odd.
Odd.
Okay? So we have proved which one? The contrapositive statement. Now proving contrapositive is same as proving this, so we are done. Did you get it? Huh? Guys? Should we move to next one?
Yes.
Yes, sir.
Yes, sir. Yes, sir.
Proof by contradiction. What is proof by contradiction? What is proof by contradiction? Assuming the thing we want to prove that is not true. But that leads to logical fallacies or problems. We consider whatever we want to prove that is not true, that is false. But if we consider that is false, we get lot of problems, fallacies. So actually, it cannot be true. It is definitely true. So this is called proof by contradiction. Did you get it? Did you get it?
Yes, sir.
For example, we want to prove root 2 is an irrational. Root 2 is an irrational number. Okay? So what is the negation of this? Assume root 2 is a rational number. We assume this one is false. Okay, guys? Do you have any query?
No.
Okay.
So we can write root 2 is equal to a by b, where a and b does not have any common factor and both are integers. It is important. We consider a and b does not have any common factor. you might ask me, sir, is it possible to write? Of course, definitely it can be possible to write. For example, let's take uh, 12 and 30. Do they, do the numerator and denominator have common factor?
Yes, sir. 2.
What is the common factor?
2, sir.
So if you multiply by
2,
2,
3.
if you divide by 2, we get 6 and 15. Still we have common factor, right? What is the common factor?
3, sir.
3. So if you divide by 3, what we get? 2 and 5. Is there any more common factor?
No.
So any rational number can be represented to this kind of non-common or simplest form. Do you agree with me or not?
Yes, sir.
So right now the A and B is this kind of form. It is important, remember. Okay, guys?
Yes, sir.
Now square this. 2 equal to A square by B square. So A square is nothing but 2B square. Do you agree with me or not?
Yes, sir.
Then what is this number? This one is?
Even, sir.
Then what is A square?
A square is also even.
Acha. From previous theorem, what do we get? If x square is an even number, then x is also an even number. Do you get it? Do you get it?
Yes.
A is an even number. A is an even number. Okay, guys? Can you write A equal to twice C? Where C is an integer. Can we write it? Can we write it?
Yes, sir.
So what is A square?
4C square.
Is equal to what?
Even number.
Equal to what? A square equal to 2B square. So 2B square. Do you agree with me or not? A square equal to 2B square, A square equal to 4C square. So they all
Yes.
three are equal. So if you consider up to this, what can we write? 2C square equal to B square. Do you agree with me or not?
Yes, sir.
So 2C square is even number. Do you agree with me or not?
Yes, sir.
So B square is also even number. Do you agree with me or not?
Yes, sir.
Then B is the even number. Do you agree with me or not? From the same theorem. If x square is an even number, then x is an even number. Do you agree with me or not?
Yes, sir.
Then let's consider this and this. A is an even number and B is an even number. So definitely they must have one common factor. What is that?
So,
2. Now we have already considered A and B does not have any common factor. So it is what? It is a problem, right? So here we have a problem. Why this problem arises? Because we consider this one is a rational number. So this is the problem. So we have proved root 2 is an irrational number. Did you get the proof? Guys,
Assumptionটা স্যার false proof করতে হবে।
assumptionটার কারণেই তো ultimate problemটা হয়েছে. So assumption
Right.
is actually wrong. So indeed root 2 is irrational number.
স্যার assumptionটা false proof করতেছি আমি।
আমরা যেটা assume করেছি এটাকে false proof করছি, মানে যেটা proof করতে চাচ্ছি
Right.
সেটা proof
Yeah.
করব. Okay guys, so এবার let's go to next example. Proof by finding a explicit or concrete example. So in this case, we are trying to find out an explicit or concrete example. So remember, proof by contradiction, contrapositive, induction, direct. Those are very versatile proof techniques. Almost anywhere you can use interchangeably these proof techniques. But construction, non-construction, those are actually very special case type of proof techniques. Not everywhere you can use. For example, let's try to prove this. Irrational power to an irrational number might be rational. You want to prove this? Might be, not always. Might be. So we have to find out a concrete example. So finding that concrete example technique is called proof by construction. You are constructing. You are finding an example. So how can you prove that one? How can you prove that one? Let's consider a equal to root 2. What is this number? Is it rational or irrational? It
Irrational.
is irrational. And b equal to log 2 base 9. And it is also irrational. Okay, guys? Now, what is a to the power b? Root 2 log 2 base 9. So, what is this? Root 2 log 2 base 3 square. So, what is this? This is nothing but root 2 2 log 2 base 3. If you know the property of the log, we know that log b base a base c is nothing but c can come forward c log b base a. We did this thing. So this is nothing but again root 2 square to the power log 2 base 3, because we know that a to the power bc is nothing but a to the power b to the power c. So it is nothing but 2 to the power log 2 base 3. So what is this? What is this? This is nothing but 3, because log b to the power log b base a is nothing but a. So we got irrational to the power irrational some integer or rational number. So we are done. Did you get it? Did you get it?
Yes, sir. তাহলে কি স্যার proof হয়ে গেল?
Prove হয়ে গেল, কারণ might be see the language, might be rational. So one example is more than enough to prove this.
Oh, okay.
Not always, might be. Okay. Let's talk about proof by non-construction. Finding implicit example, not direct example, implicit example. So let's try to prove this again using non-construction. In this case, we don't know whether it is correct example or not, but we are going to use logic in such a way so that it becomes an example. How? Let's consider root 2 by 2. Let's consider root 2 by 2. Okay, guys? If it is rational, then done. We are done. Because it is already rational. But আমরা জানি না, we don't know whether it is rational or not. So let's consider consider root 2 by root 2 is irrational. Okay, then take again root 2 to the power root 2. So it is irrational and it is also irrational. So what is this? Root 2 into root 2, which is nothing but root 2 whole square, which is nothing but 2. So we are done. So this is the dummy case. Dummy case. If it is the case, then we don't need to prove. So we have to go alternative. We consider it is an irrational. If it is still irrational, we get an example where irrational to the power irrational is rational or integer. So we are done. Did you get this proof?
স্যার এখানে কি একটা এক্সাম্পল
Example,
দেখালেই
yes, we
হয়ে
are
যাবে?
giving an example, but actually we don't know the status of the example.
Right.
We are giving an implicit example, but we don't know the status of the example. That is the catch. Got it? Now let's go to last example, then we'll stop today here. From the next class, we'll start finite automata. Okay, guys? So what is the last example? What is the last example?
Exhaustion. Proof by
exhaustion.
exhaustion.
Considering all the cases. So let's try to prove this. The square of an integer should be divisible by 4 or under 1 when divisible. So we already see here we have two cases. It either divisible by 4, case 1, and or remainder 1 when divisible by 2, case 2. Okay, guys. So how can you prove that one? An integer can be what? Can be two types. What are those? It can be even or odd. Do you agree with me on that? An integer can be even or odd. Do you agree with me or not?
Yes, sir.
Yes, sir.
So case 1, if even, then we can consider n equal to twice c, where c is also an integer. Do you agree with me or not?
Yes, sir.
So
Yes, sir.
n is square equal to 4c square, and it is divisible by 4. So it is also divisible by 4. Do you agree with me or not?
Yes, sir.
So case 1 is proved. It's divisible by 4. Now let's go to case 2. If odd n equal to twice c plus 1. Okay, where c is integer. Do you agree with me or not? So what is n square? Twice c plus 1 whole square. What is this? 4c square plus twice c plus 1. So twice c plus 1 plus 1. What is this?
Even,
What is
sir.
this? Even. Divisible by 2
And
or
remainder
even.
1.
So what would be the remainder? Remainder is 1. So we prove
1.
case 2. We are done.
Yes, sir.
So this is the end of proof techniques. Almost all the major and most important proof techniques we have covered, and we have given example. Do you have any question? You can ask.
স্যার প্রুফ বাই নন কনস্ট্রাকশনটা আরেকবার বুঝাইলে ভালো হতো।
Proof by non-construction এর সাথে proof by construction এর difference See, in proof by construction, we give a concrete example. That means root 2 to the power log 2 base 9, which is actually irrational to the power irrational, is actually an integer or rational number. We know this, the status of this example. Okay, guys? We know the status of this example, that it is our desired answer. It
Yes,
is
sir.
our desired answer. So we constructed an example. On the other hand, proof by non-construction, we don't know whether it is actually rational or irrational. But we consider both cases. If it is rational, that's fine. We got the answer. It is the dummy case. So we'll consider it is irrational. If it is irrational, still we got another answer. So we are very exhaustive about all the possible movements. That's why explicitly, without giving any example, we prove the theorem. Did you get it?
Yes, sir. Yes, sir.
Okay. We don't know whether root 2 by root 2 is irrational or rational. But it does not matter. Still we will get an example. Done?
যদি এটা স্যার ইন্টিজার না আসতো স্যার রেজাল্টটা
Integer তো আসলো না, আসলে তো আর হলো না proof by construction. Non construction তো it would not be proved by non construction. Done, guys? Done. Any more questions?
স্যার আমরা এই রেকর্ডিং গুলো কিভাবে পাবো পরে?
I'm going to share the YouTube channel.
আচ্ছা,
Any more question?
no sir.
Okay, then goodbye. Have a nice weekend. Okay, guys. See you in the next class.
বাই বাই
Bye bye.
Thank you sir.
Bye.